Welcome guys, good morning, afternoon, evening. So today we'll be doing a past paper simulation actually, and this is from, if I'm not mistaken, this is from 2021-2022, okay, semester 2 exam. And this is the past paper questions, okay, so there's question 1, question 2, okay, you can see question 2. Right, never mind. Question 2, question 3, and question 4. And you're given the appendix. So appendix usually will just be they give you the moment of inertia of certain shapes, right? Mainly the shapes you to worry about are circle, rectangle, and triangle. Semicircle also, if you want to worry about it. And they've given the moment of inertia as well. Okay? And the central location. Okay? So I'm gonna do like this. I'm gonna do one question one by one. Okay? So it'll be part by part. I'll record a video, and of course we'll solve them, and yeah, we'll post it in part by part. So that means question 1 I'll put as part 1, question 2 as part 2, question 3 as part 3, question 4 as part 4. Okay? So without further ado, let's go and solve for question 1 first and foremost. Okay? So question 1 asks us to determine the center of the shaded area shown in figure 1. Okay, so this is figure 1, and state the answer as a coordinate, clearly indicate which element was used. So this is part A. Okay, so if we go to our app, so let's go for question 1 first. Okay, I'm gonna draw the axis. I think, okay, better. Okay, so this is our y, this is our x. Okay, so we have two curves. Okay, so I'm gonna draw it here. Okay, first one, second one is a curve also. Sorry. Okay, so let's see what else also we have here. 0 to 4. Okay, so over here 0, and this point here is 4. Okay, and here is 2 and 16. Okay, 2 and 16, so it would be here would be 2, and here would be 16. Okay, and for the blue curve, the equation is what? Y equals to 4x plus 2. So whereas the orange curve, it's y equals to x cubed over 4 plus 2. Okay, so x cubed over 4 plus 2. Okay. Alright, so yeah, we already plotted the curve. They want to find the center of the shaded area. Okay, so to find the center of the shaded area, okay, by integration, and our shaded area I didn't shade yet, I'm so sorry, but this is our shaded area, which I shade in green. Okay, so in order to find the centroid, yes, to find the center of a shaded area, okay, how are you going to find the centroid? That's our x bar and y bar. How are you going to find that? Okay, it's actually fairly simple. So I suggest we take the vertical element. Okay, we take the vertical element, and the vertical element, we know that this is dx. Okay, and how about the height of the vertical element? So the height of the vertical element actually is y1 minus y2. So its height is dependent upon equation y1 and y2. So what is y1? Your y1 actually is this equation. This is your y1. Okay, because this is on the top of the curve, right? So it's the dominant curve, right? So because y1, usually we take the one on the top, and then this one here is your y2. Okay, this is your y2, so this is your bottom. Okay, so therefore your y1 and y2 is just simply 4x plus 2, right, minus x cubed over 4 plus 2. Okay, so you simplify it, you end up having 4x minus x cubed over 4. The 2 will just cancel out, right, at the end of the day. Okay, so yeah, we took the horizontal element, alright, and we already have our dx, we already have our height, right, which is just 4x minus x cubed over 4. Okay, so to find centroid, if you guys remember, for centroid, if you're finding for x bar, it is always the integral of x tilde dA over the integral of dA, right? For y, for the centroid for y, is just simply the integral of y tilde dA over the integral of dA. Okay, and we're gonna get into a bit about x tilde and y tilde. Okay, so don't worry so much about x tilde and y tilde for now, we'll get into it later. But let's find dA first. Okay, so our dA is what? Our dA is just equivalent to y1 minus y2 times dx. So our dA is our differential element. So y1 minus y2 already found earlier, which is just simply 4x minus x cubed over 4 dx. Alright, so when we integrate our dA, okay, when we integrate our dA, so that means to say we integrate 4x minus x cubed over 4 dx. So our limits for integration will be from 0 to 4 with respect to x, because we are chopping along the x direction, right? We're chopping along the x direction, so it'll be from 0 to 4. So we put our limits of integration, okay, and then we solve the integral. So find the antiderivative, which will just simply become 4x squared over 2 minus, this is over 4 is a constant, so you can put this 1 over 4 times x to the power of 4 over 4. Okay, and then you put here 4 and 0. Okay, so you substitute the limits inside, and once you do so, your final answer should be 4 over 2 times 4 squared minus 1 over 4 times 4 to the power 4, 4 to the power 4 over 4, 16. Okay, so here is 16. And then of course you subtract with 0, because when you put 0 inside, it becomes 0. So the final answer is 16. Okay, did they mention any units? They give the units, so don't forget to put your units, meter squared. Okay, so we've already found our dA. I'm just going to erase the working, okay, so that we have space for other parts. I'm going to erase this real quick. So we got 16. So just wanted to say that our integral for dA already is computed to be 16. So 16 meter squared. Okay, so we're done. So now we proceed to the next step. The next step is to find the x tilde and the y tilde. Okay, so here the center of each element, we already know it's just basically equals to x tilde and y tilde, right? The position from the center of each element. So the thing is, for each element, if you are cutting the horizontal vertical section, right? So this x tilde actually will follow the x coordinate. Okay, let me use a different color. Okay, so for example, this is your, wait, I don't think you can see this. Let me use a different color. Yeah, let me use red. Okay, okay, right, okay, sorry. So okay, it's a little bit tricky, but yeah, okay. So you can see that for your x tilde here, for each element, it depends on the position of your x coordinate. Whereas for your y tilde, it's not just the position of the y coordinates, actually between the position of your y1 here and your y2. It depends on your y1 and y2 actually. Okay, so that means your x tilde is just simply x. Alright, whereas your y tilde is your y1 plus y2 divided by 2. So your y1 is what? Your y1 already we know is 4x plus 2. y2 is this. So if I were to simplify, it just becomes 4x plus x cubed over 4 plus 2 becomes 4. You divide it by 2, which would give you 2x plus this one 1/4 divided by half, 1/4 or divided by 2, 1/8. Okay, so it becomes 1/8 x cubed plus 2. Okay, so you already got your y tilde and x tilde, and I can simplify it. Actually, I can save space by writing it like this. So it's supposed to be x cubed over 8 plus 2x plus 2. Okay, so with that being said, then our next step is to find the integral. Alright, so this integral we're going to find first, which is just simply x tilde dA. Okay, wasn't clear stuff. Okay, so again, don't forget your limits here, 0 and 4. So we put our limits 0 and 4, x times dA. So our dA is 4x. Yeah, so basically just simply 4x minus x cubed over 4 dx. So then you put in the limits, so it becomes 4 and 0, 4x squared minus x to the power of 4 over 4 dx integrated. So you would have what? 4x cubed over 3 minus 1/4 times x to the power of 5 over 5. Then you put in the limits 4 and 0, and then your final answer will be, let's see, so it becomes 4 over 3, 4 cubed minus 1/4 times 4 to the power of 5 over 5. So yeah, you'd get 5112 over 15. This one you put meter cube. Okay, because why you put meter cube is our x already is in meters, okay, and then our dA is in meters squared, so therefore the unit will be meter cube. Okay, so let me just erase this. Okay, to have space. So it's just 5112 over 15 meter cube. Okay, now we do the same for the y tilde. Okay, I think I'll need to erase a little bit to have some space. Okay, so hopefully we have space. Right. So we do our y tilde dA, which is just we put the integral limits 4 and 0. Okay, so it becomes x cubed over 8 plus 2x plus 2 times 4x minus x cubed over 4 dx. Okay, so I'm gonna have to erase this x cubed plus 2x plus 2. Okay, so okay, so let's try to solve it. We first simplify the expression, so it becomes 4 and 0, so this x cubed times 4x becomes 4 over 8, x to the power 4 becomes 1 over 2, right here, 1 over 2 x to the power 4 minus x to the power of 6 8 times 4 is 32, okay, plus 8x squared, and then minus 2 over 4 becomes 1 over 2 x to the power of 4, okay, plus 8x minus half x cubed, okay, dx. Alright, so you have this integral, and once you integrate it, you end up having what? You have 1 over 2 times x to the power of 5 over 5 minus x to the power of 7 over 32 times 1 over 7 plus 8x cubed over 3 minus 1 over 2 x to the power of 5 over 5 plus 8x squared over 2, okay, minus 1 over 2 x to the power of 4 over 4, and then you put in the limits 4 and 0. So I'm going to use my calculator to get the answer, so let's have a look. So 1 over 5 minus 1 over cube minus 1 over 10 x to the power of 5. Oh, by the way, I noticed you can actually cancel these two. I just came across my mind that these two can be cancelled off straight away, right? Yeah. So it makes our problem a bit simpler. Okay, let's proceed. Okay. X squared x to the power of 4. Okay, so we get hold on, we get 2720, so 2720 over 21, okay, meter cube, okay, and you put 0, you'll end up having the answer is 0, okay. So that means our answer for this, okay, is already given to us. Is just 2720 over 21 meter cube. Okay, so yeah, 2720 right, great. So now we can easily find the x bar and the y bar, right? So x bar is very simple. You just simply this value divided by 16 meters squared. So once you do the division, so just simplify 1 to 15 divided by 16. So it's 32 over 5, 32 over 15 meters, which is equivalent to 2.13 meters, right? So 2.13 meters. And then your y bar, okay, you just simply again, you take this value, you divide again with 16. So it becomes 2720 over 21 divided by 16. So it becomes 170, so it becomes 170 over 21, which is equivalent to 8.10, so 8.10 meters. So your centroid should be 2.13 and 8.10. Okay, so this is your x bar, your y bar. Okay, so this is your final answer supposedly, and it makes sense because it would be lying within the the area itself. Okay, like 2.13, 8.10, so it's logical. Okay, it's a logical value because it'll be lying between the area itself. So we're done with part A. Now we go to part B. So part B said to determine the moment of inertia about the y-axis of the shaded area shown in figure 1. Use the vertical element for your calculation. Clearly indicate which equation is used. Okay, so in this part A, remember, they didn't explicitly told us which element to use. You can also use the horizontal element and get the answer, actually the same answer I got, but I don't recommend it. Because why? You can see that your equation is y in terms of x, y in terms of x. So if you use the vertical element, you already have dx already there, right? So it means it's easy to integrate respect to x, okay, because you already have an expression of x. If you were using the horizontal element, that means that you have to integrate respect to y. So you have to change the equation to be x equals to a function of y, which is a hassle, right? And it's not recommended at all. So don't try to do things or make your life more difficult, okay, when you're actually fighting against the time. So we are fighting against the time here, so that's why we use the easier element. But for part B, they ask you to find a moment of inertia in figure 1. Use the vertical element for calculation. Clearly indicate which equation is used. Or send a moment of inertia about the y-axis. Okay, so for moment of inertia about the y-axis, if you want to compute for moment of inertia on the y-axis, you have to remember this one important thing, okay, and that is, I'm gonna erase this answer, by the way. I think this answer, I'll keep dA, by the way. dA I think should be there, but it's okay. Never mind. Let me erase all this. Okay, so if you want to find, I forgot to change this to B, right? Because we're now not doing A anymore, we're doing part B, right? Okay, so for part B, alright, for moment of inertia, okay, if you want to determine moment of inertia IY, obviously the element that we're supposed to use, okay, typically is for the vertical element, okay, with dx, and IY, the moment of inertia is what? It's just simply the integral of x square dA. Okay, simply the integral of x square dA. Okay, so we already have a vertical element and we already have our dA. Our dA is just simply 4x minus x cubed over 4 dx, right? So that means our IY is really easy to find. Okay, so we're integrating. Again, our limits are between 4 and 0 because our dA is respect to dx, right? So become 4 and 0. You're multiplying x squared, and it's just gonna be 4x minus x cubed over 4 dx. Okay, so once you do the integration, okay, don't forget to simplify. So become 4x cubed minus x to the power of 5 over 4 dx. So you find the antiderivative becomes 4x to the power of 4 over 4, which is just x to the power of 4, right? Okay, so and then you have here minus 1 over 4 times x to the power of 6 over 6, and then you put your limits 4 and 0. Eventually your answer is what? So it becomes 4 to the power 4 minus 1 over 4 times 4 to the power 6 over 6. So it becomes 256. Okay, so 256 over 3 meter to the power of 4, or you can also write in 85.3. If you want to write in decimal, also can. 85.3 meters to the power of 4. Okay, and usually for moment of inertia we put meters to the power of 4. Why is that the case? Because our x squared becomes meters squared. Our dA is also meters squared. So meter squared become meter to the power of 4. Okay, so hopefully that's clear. So we've already done part A and part B. Now we really have to find for part C. Okay, for question 1. So let me erase everything here, because part C is a different question. So we go to part C. So part C, determine the moment of inertia about the x-axis of the shaded area in figure 2. Clearly indicate how the area is divided into segments and what are the equations that are being used. Okay, so we have a very simple shape. Okay, I think I'll have to redraw it in the paint software. So let me just redraw it. So if I'm not mistaken, it's a trapezium, okay, which looks like this. Okay, so the trapezium. Okay, what else? Okay, let me draw the x and y axis first. So here is your x, here is your y axis. Okay, and what else also? Oh, sorry, this one. Okay, so 5. Okay, so let's see the here circle. We also have a circle as well. Okay, I think I have to highlight the fact we have a circle in our drawing, a hole actually. Alright, and let's write down the limits. 5. Okay, so this is 5, -4, -4, -2. Okay, so -2 will be here, by the way. So -2 is the location of the center of the circle itself. Okay. What else? -8. Wait. This one will become -8. 6. 6. This will become 4. Okay, coincide with the circle also, or the hole actually. Okay, so now we write the dimension. So here is 5 meters, here is 4 meters. I think this side is, sorry, this one is 6 meters and 8 meters. Okay, so 8 meters from here to here is 8 meters. Okay, so they're saying that from here to here is 8 meters, and from here to here is 6 meters. Okay, so this part to this part is 6 meters. Okay, anything else I missed out actually regarding this problem? 6 meters, 8 meters, 4 meter, 5 meter, 1 meter. I think the radius of a circle, I forgot to mention that this is 1 meter. Okay, so the question asks us to find the moment of inertia. Okay, so to find the moment of inertia on which axis? X-axis. Okay, moment of inertia on the x-axis. So they want to find the moment of inertia. Okay, they want to find the moment of inertia of the entire figure. Okay, in the x-axis, respect to the x-axis. So how do we find the moment of inertia for the x figure? Is basically through the parallel axis theorem. So basically, the moment of inertia is just Ix equals to Ix prime. Okay, plus a dy squared. Okay, so this Ix prime actually is the what? Okay, I think if I use a, here will be very confusing. But this Ix prime, what is it referred to? It's basically referring to moment of inertia. So moment of inertia for each shape. Okay, and our A here, okay, is referring to the area of the shape. Okay, moment of inertia for each shape in its centroidal axis. Okay, I will explain in a bit what do you mean by centroidal axis. Okay, area of the shape and this one is distance from centroidal axis to reference axis. Okay, to reference axis. So I'll explain this in a bit actually once we do the calculation sectioning. So first and foremost, let's do the sectioning. So we can easily section the trapezium into a triangle, right angle triangle. So I'll call this as section 1. I'll just label it here as shape 1. Okay, shape 2 and shape 3, which is a hole. Okay, so do bear in mind that shape 3 is a hole. Okay, so let's do for each shape one by one. So for shape 1, okay, for shape 1 is a right angle triangle. Okay, and if we look in our what do you call it, our appendix, okay, which I have it right here. If we could zoom in a little bit, would be nice. I think, yeah, it's okay. You can see that actually I think we can also zoom it from our slide. I think it's better. Okay, alright. Okay, so if you actually go here for triangle, it's 1/3 of the perpendicular distance from the height, right, the centroid. Okay, because we want to put our reference axis, typically it's a good idea to put our reference axis at the centroid itself. Okay, so our reference axis would be okay, I think I'll put it in gray color, would be here. Okay, so this would be our reference x-axis. Okay, this is our reference x-axis, which I put as call it x prime. Okay, it's a reference x-axis, and basically the reference x-axis is 1/3 of it. Okay, 1/3 from this particular base. Okay, so this is our shape 1. Alright, and you'll see in a bit why am I doing this. So basically, if we draw a triangle, our reference axis is here, x prime. Okay, and it's 1/3 of the entire thing, which is just basically 5 meters plus 4 meters, because the whole thing is just simply 9 meters, right? Okay, so to find the moment of inertia for a triangle, right, we find the Ix prime first. So that would be Ix prime is just equals to, if we go into appendix, I think it's 1/36 BH cubed. This for Iy, so Ix would be 1/36 because we are concerned with the height, so it would be BH cubed also. Okay, so it becomes 1/36 times our base is what? Our base is 6 meters, so times with 6, h is 9 cube. Okay, so it's just 1/36 times 6 times 9 cube would be about 121.5 meters to the power of 4. Okay, then the area of the triangle itself is just simply 1/2 times, okay, I think this is 6 meters, I forgot to mention it here, 6 meters, so it's 6 times 9, so it become 1/2 times 6 times 9 becomes 27 meters squared. And how about your dy? Okay, so our dy is what in this case? So because our reference axis is here, so our dy again is the distance from this axis, our centroidal axis x prime, to the original axis x. So this is our dy. Okay, so in this case, since I mentioned that this is 1/3, right? This is 1/3 of the original axis, right? So this is basically 3 meters. Okay, and the whole thing is 9 meters, so this is 3 meters. Okay, so it's 3 meters, and from here is 5 meters. Okay, from this part to the reference x-axis is 5 meters. So it's basically 5 minus 3. So it's just 5 minus 3. Okay, this is a 5, not an s here. So it's supposed to be 2 meters. So your Ix, okay, for shape 1 is equivalent to 121.5 plus 27 times 2 squared. So it's just 121.5 plus 27 times 2 squared, which is 229.5. So it's just 229.5 meters to the power of 4. Okay, so I'm gonna erase all this because we don't really have much space. So I'm just going to write it here. So shape 1, we already found the moment of inertia, which is, so shape 1, okay, it is 229.5 meters to the power of 4. Okay, then let's go for shape 2. Okay, so for shape 2, okay, so for shape 2, it's the rectangle. Okay, so for rectangle, what we know so far is the center actually is just here. Okay, so rectangle, if I draw the rectangle, okay, I'm going to draw the rectangle, the center is just in the middle. Okay, so we know the whole length is 8 meters, right? We know it's 8 meters. So this is the centroidal axis, x prime, okay, which is just directly in the middle, so it's very nicely fitted. Okay, and basically we know the length of the rectangle is 9 meters, right? The whole thing is 9 meters. Okay, the whole thing is 9 meters basically. Alright, so to find the Ix prime of the rectangle itself, okay, you just 1 over 12 BH cube. Okay, because you look at our appendix, for rectangle just 1 over 12 BH cube for Ix. So 1 over 12 BH cube. So your B in this case is 8. Okay, your H is 9, so it becomes 9 cube. Okay, so we'll be leaving you an answer of 1 over 12 times 8 times 9 cube. So 486. So it's about 486 meters to the power of 4. Okay, then we know the area of the rectangle is just simply 8 times 9. Okay, so it's about 72 meters squared. How about your dy? What is your dy? So your dy again is the distance from the reference x-axis, so it's here, but it's just slightly above. Okay, so this is your x prime to the rectangle, right? And this is basically your dy for shape 2. Okay, this is dy. So I told you it's 9 meters, right? And half of it is obviously gonna be half of it is what in this case? Half of it we know it's 4.5 meters. Okay, we know it's 4.5 meters. But since the rectangle is not actually even on the x-axis, it's just simply 5 and 4 meters. So therefore, the dy is actually somewhere a little bit on the top. Okay, so it's gonna be what? How are you gonna compute the dy? So it's just simply because our dy is simply here, so it's gonna be what? How you compute it? It'll be 5. Okay, 5 meters. Okay, and minus 4.5. Okay, so minus 4.5. Okay, because 4.5 is the center, so then you'll get the final answer. So 5 minus 4.5, which is 0.5 meters. Okay, so therefore your moment of inertia for shape 2 is Ix equals to 486 plus 72 times 0.5 squared. So it becomes 486 plus 72 times 0.5 squared. So it's supposedly 504. Okay, so it's 504 meters to the power of 4. So shape 2, we already found the moment of inertia, which is just 504 meters to the power of 4. Okay, so that's for shape 2, already done. Now for shape 3. Now shape 3 is a bit interesting because now we are dealing with a hole actually, right? And let's try to solve for it. So for shape 3, since it's a hole, okay, for a hole actually, the formula is still the same, will still apply. So we have a circle. The radius is r is 1 meters. Okay, and its centroidal axis would be here lah, x prime. Okay, so let's solve for ix prime for the circle itself, which in the appendix is given to us as 1 over 4 pi r to the power of 4 for full circle. So it's 1 over 4 pi r to the power of 4. It's just 1 over 4 pi times 1 to the power of 4, which is just, 1 over 4 pi meters to the power of 4. Okay, great. Area of the circle, we know is just simply pi r square, right? So just pi times 1 square, which is just simply pi meter squared. Okay, how about your dy? What is your dy? So basically the circle centroidal axis is here, right? X prime is here. So I think I'm going to use a different color. So I'm going to use maybe orange. So from x to x prime, it's going to be negative because it's going downwards. And it's actually here, it's already given, it's because it's just negative 2 at this point, right? So it's basically negative 2. Okay, so dy is just negative 2, right? So just negative 2 meters because it's going downwards. Okay, there's a distance between the x-axis and the x prime. Okay, so all in all, your ix would be 1 over 4 pi plus pi times negative 2 squared. So just 1 over 4 pi plus pi times negative 2 squared. So it's 17 over 4 pi meters to the power of 4. Okay, so for shape 3, we've already identified it. So shape 3 is equivalent to 17 over 4 pi meter to the power of 4. Okay, so if you were to add up all the moment of inertia together in the x-axis for I1, I2 and I3, so moment of inertia in the x-axis is just simply I1 plus I2. Okay, but here's the catch. Because shape 3 is a hole, you'll actually have to subtract with I3. Okay, it'll be negative. So it's just simply 229.5 plus 504 minus 17 over 4 pi. So your final answer would be 229.5 plus 504 minus 17 over 4 pi. So it becomes 720 meters to the power of 4. So this is basically your moment of inertia along the x-axis. Okay, so going back to our question here in tutorial 1, I think that's about it for tutorial for question 1. Okay, so I'll be recording for question 2 and question 3 also, and question 4 as well. And yeah, hopefully this is very helpful. Hey guys, Assalamualaikum. So we're back again at question 2 for this exam paper. So let's do for A, B and C. Okay, so let's look at question A. So question A. If the cable AB in figure 3 has a tension of 100 newtons, okay, determine the weight of the beam AD and the support reaction at AC. At A and C. Support reaction at A and C means what's the support reaction? Because I think C is a slot, right? Point G, the center of the beam AD itself. Okay, the center of the mass of the beam AD itself. Okay, so for this question, okay, sorry, go back to the question. So for question 2, part A, alright, okay, we're gonna draw the free body diagram. So this is the free body diagram of the beam itself. Okay, so what we have here, we have a roller. Okay, so we have a roller. So for the roller, okay, we're gonna write it as FA. Okay, and then we have the tension from the cable, which is 100 Newton. Okay, so I'm gonna mark it in white color. So this is the tension of the cable. This is about 100 Newton, and it is an angle of 15 degrees. Okay, so basically 15 degrees. Okay, so this is about 15 degrees, and the whole angle that the beam makes with the horizontal is 30 degrees. Okay, great. What else also we have here? Okay, then we have the slot at C. Okay, so the slot at C, okay, the slot at C actually, right, it has a force that's acting on it. Okay, and if I'm not mistaken, this is the only force basically that's acting on it. Yes, so this is the only force that will act on it. So it would be acting at here. Okay, so this is the slot force at C. Support reaction, we call it as FC. Okay, and you want to find the weight of the beam also, right? Weight of the beam AD. Okay, so the weight of the beam also, I'm gonna draw a force here. Okay, which would be the weight of the beam. Okay, and then we mention the dimensions. So here, dimension from here to here is 0.5 meters. Okay, then here to here is 0.2 meters, 0.2 meters, and then the last one is 0.3 meters. Okay, so 0.3 meters. Okay, so we can see that we have two unknowns that we want to find. Actually, three unknowns. Okay, we do not know what's the roller force at A. Okay, so we do not know the roller force at A, we do not know the weight, and we do not know the FC, right? And the question wants us to find the weight, and they want us to find the FC, the force FC. Okay, and since our equation of equilibrium is limited by three equations, okay, so let me just draw the positive x and positive y axis. So we need to say that we're limited with the summation of fx equals to 0. Okay, then for summation of fy equals to 0, and of course the moment, okay, in this case we can take our moment at point A to be equal to 0. Okay, so this is what we're limited to. Alright, so how are you going to find it? Okay, so let's see. If we consider for fx, right, what we do have here is that we have the cable, the tension of the cable, which has an x component. Okay, so you'll have an x component here, right, which will just simply be 100 cosine of 15 degrees. Okay, and then W and FA are purely in the y direction, so no need to worry about that. Now for this FC, okay, this FC, here's something I want to bring your interest to. This FC has an angle, right? And this angle is exactly 30 degrees. Okay, so that means to say it also has a vertical component and a horizontal component. Okay, so in this case it will be easy for us to find for FC because the only force in the horizontal direction will be due to the tension of the cable itself, okay, and of course due to FC, right? So W and FA is not any issue at all so far. Okay, so we're gonna take the summation of fx is 0. Okay, summation of fx is equals to 0, and in this case we can say that 100 cosine of 15 degrees, which will go in the positive direction, minus fc. Okay, so sine 30. Okay, so sine 30 is equals to 0. So that means fc sine 30, okay, is equals to 100 cosine 15 degrees. Okay, thus you got your fc, the reaction force, to be 100 cosine 15 divided by sine 30. So your FC is 193.185 newtons, and if you take it to 3 significant figure, just 193 newtons. Okay, so this is your FC. Alright, because that's what the question asked. First part of the question, you want to find support reaction A and C. Okay, and they wanted to find the weight of the beam. Okay, so they're interested in finding the weight of the beam itself. So I'm just gonna write here your FC value, which is just simply 193.185 newtons. Okay, or you can just say it's 193 newtons. Alright, so we'll erase this. Let me just get to brush size. Okay, then now to find for the weight, it may seem a little tricky, but I suggest we take the moment at point A to be equal to 0. So that means that we don't have to worry about FA at all, or any effect of moment due to the tension of the cable itself. So if we take the summation of moment at point A to be equal to 0, okay, I forgot, I made a mistake here. Suppose I want to put the counterclockwise as positive. Okay, so it's supposed to be counterclockwise as positive. So therefore in this case it would be the weight, which is just negative W, and this is 0.5 cosine of 30 degrees, right? So multiply it with 0.5 cosine 30 degrees. Okay, that would give the clockwise moment. And FC, because FC is lined perfectly to the bar itself, it would give a counterclockwise moment, so it would be plus FC, and our distance actually from point A is 0.5 and 0.2, so just simply become 0.5 plus 0.2. okay, and yeah, equals to 0. So this one, obviously the FC would give the counterclockwise moment, our weight here would give the clockwise moment, right? So they'll of course will give the moment to be 0. Okay, so that is to say 0.7, so 0.7 FC equals to 0.5 cosine 30 degrees W. So then W is equals to 0.7 So FC is 193, but I put 185, yeah, because we want to avoid any round off mistakes. Alright, to make sure our answer is accurate. So it's 0.5 divided by 0.5 cosine 30 degrees. So your weight would be 0.7 times 193.185 over 0.5 cosine 30. So your weight of the bar would be 312.299 newtons. So you can just simply put it as 312 newtons. So your weight of the bar is 312 newton. Your FC is 193. Okay, so that's your first part done already. It's just 8 marks, so it's not that complicated. Now for your second part, part B, which is a 3D problem, and this can get a little bit tricky, but not to worry. Alright, so let's erase this first. Okay, so for part B, okay, the signboard in figure 4, okay, or this figure, has a weight of 80 Newton. Okay, they're given the weight of the signboard with center of mass at G. Okay, good to know. And determine the X, Y, Z components or reaction and the ball and socket at joint D. Okay, so ball and socket at joint D. Alright, and we have the two cables that's holding the signboard, right? And the tension, the wires AB and AC itself. Okay, so they want to find the XYZ component reaction, the ball and socket joint, and of course the tension from both the cables, right? And yeah, so the first things first, to approach this problem, always don't forget to draw your free body diagram. So let me draw my free body diagram real quick. So since it's 3D, right, we're gonna use the 3-dimensional axis. So we're gonna do it like this. So this is your X, this is your Y, this is your Z. Okay, and then for this case, the signboard, I'm gonna draw a signboard like this. Okay, so it's a signboard. Okay, so a signboard has a weight of 80 Newton. Okay, they already mentioned the weight of the signboard itself, so it's just simply 80 Newton. Okay, great. And then we have the cables, right? We have the cables that are here, right? Okay, and the cables themselves, they have given the direction to be what, 1 and 2. So from here is 2 meters. Okay, so they give the position vector. Here is 2 meters, here is 1 meters. Okay, this one is cable AC. Okay, so it's cable AC. And then for here, the height here is 2 meters, I think, if I'm not mistaken. And here is 1 meters, yeah. Okay, here is 1 meters. Okay. And then we have the ball and socket joint at this point. So ball and socket joint, you must remember for ball and socket joint we have 3 constraints. Okay, so the constraints are that you couldn't move in your X direction, so there will be a support reaction X, which we call it as Fx. Okay, we also cannot move in the Z direction, so just Fz, and also we cannot move in the Y direction, so this is just simply your Fy. Okay, whereas for the cable, the tension, we have here TAC and we have here TAB. Okay, so now there comes the question, how are we going to solve this problem? So for 3D case, we actually have 6 equation equilibrium. Okay, we need to say that our summation of Fx equals to 0, summation of Fy equals to 0, summation of Fz equals to 0, and then summation of Mx equals to 0, summation of My equals to 0, summation of Mz equals to 0. So we have 6 equations, okay, to help us find 6 unknowns. The number of unknowns we have here, okay, is 1, 2, 3, 4, 5. 5 unknowns, right? We have the tensions, we have the support reactions, so it's 5 unknowns, and we have 6 equilibrium equations. So this equation we can start to solve. Okay, so how do we solve this? First things first, I want to find the tension vector respectively. At least I want to express it in terms of its x, y, z components. And how are we going to do that? It's actually fairly straightforward. So we have our vector first of all, AB. Okay, so our vector AB, okay, if we write a position vector, it's simply what? Oh, I forgot one more important thing actually. So this one is here is 1 meters and this is 1 meters, right? According to the question, am I correct? Is this what I asked for? 1 meter and 1 meter. Okay, yes. Alright, great. So for AB, if we write it in the x component, it has moved by 1 meter. So it's basically, you write it in I. Okay? And then in terms of J, because it's going from this side, so it's negative, so it becomes minus 2J. Okay? And then in terms of K, has gone up by 2 meters, so it'll be plus 2K. Alright, and this is in meters, right? So for AC, okay, similarly for AC, it's actually, in terms of I, it's negative, yeah, so it becomes negative 2I, so it becomes minus 2I. And then for J, it becomes minus 2J. And then for K, it is plus K. Okay, so there, AC. Then you find the unit vector for AB and AC. Okay, so the unit vector of AB actually is pretty simple. So let me write it like this. So unit vector of AB, which I'll call it as UAB, alright, is just 1 over the magnitude of AB multiply with AB, the vector AB itself. So 1 over the magnitude. How do we find magnitude? It's very simple. It's just the square root of the coefficient of I, J, and K, meaning to say just 1 square plus negative 2 squared, okay, plus 2 squared, okay, multiplied with I minus 2J plus 2K. Okay, therefore your final answer would be 1 over square root 1 square plus negative 2 squared plus 2 squared. This is 1 over 3. So it's just simply gonna be 1 over 3I minus, let me just write it nicely, minus 2 over 3J plus 2 over 3K. And remember, in vectors, you can just express it very simply. You can express it like this, as 1 over 3, negative 2 over 3, and 2 over 3, which I'm gonna do actually. Similarly for UAC, okay, it's just simply the 1 over the magnitude of AC, okay, times AC itself, the vector AC. So as usual, same steps. So just 1 over the magnitude becomes negative 2 squared plus 2 squared plus 1 squared, okay, square root times negative 2I minus 2J plus K. Okay, so you end up also, yeah, you still get 1 over 3, so it becomes negative 2 over 3I minus 2 over 3J plus 1 over 3K. So it becomes negative 2 over 3, negative 2 over 3, 1 over 3. Okay, so you got your UAC and UAB. And what's the purpose of actually getting your UAC and UAB? So let me just erase this. Why we took the trouble actually, because I wanted to find the tension vector respect to AB, right, which is just simply TAB times the unit vector of AB. Okay, because the unit vector would give the direction, you understand, and the TAB is going to give the magnitude. Likewise, also the same goes for TAC, which is just simply, you know, TAC times UAC. Okay, so quite simply I could just say it's just 1/3 negative 2/3 and 2/3 TAB, and then you have here negative 2/3 negative 2/3 and 1/3 TAC. Okay, so upon erasing all that, we start erasing everything, by the way, right? So let me just erase this real quick. Okay, so you already got your TAB and TAC, which is good. Okay, and now we can express our equations of equilibrium. Okay, so let's start with our summation of Fy, okay, equals to 0. Summation of Fy equals to 0. What do we have here? Actually, no, not Fy, sorry. I want to start with Fz actually. Okay, so summation of Fz equals to 0. Okay, so what we have here? We have here negative 80, right? So negative 80 because it's going down in the z direction. Okay, and then for TAB, we have a z component which is just 2/3, right? So plus 2/3 TAB. How about for TAC? We have 1/3. So plus 1/3 TAC. And then we also have FZ. Right? So we also have FZ. So that's equals to 0. So we have here FZ plus 2/3 TAB plus 1/3 TAC equals to 0. Okay, then we have our summation of Fy equals to 0, which is in this case Fy is positive, so Fy minus, okay, for TAB is negative 2/3, right? So it becomes 2/3 TAB, and here is negative 2/3, so minus 2/3 TAC is equals to 0. So that's our expression, by the way. And then for Fx equals to 0, we're also left with what? We're left with Fx, okay, which is positive, and then we have 1/3 plus 1/3 TAB minus 2/3 TAC equals to 0. Okay, so this is what we're facing right now. We have 3 equations, but we still have 5 unknowns, so we also need to use more equations, right, to solve the problem. So in this case, okay, let's say we bring this a little bit down. Okay, let's see, do we have extra space or not? Okay, we do have some space, great. Okay, we're not limited to space, okay, alright. So what we can do also is that we can find the summation of mx equals to 0. Okay, so for mx equals to 0, what's going to happen is either you know, in this case for mx equals to 0, what we have is that we have the 80 Newton, the signboard. So basically it will create a moment actually. The signboard will experience a moment along the x-axis, okay, which is going to obviously be rotating clockwise, right? So that's negative. So in this case, if you use your right hand rule, it's negative, so meaning to say that your be what? Let me just figure this out. The summation of mx is just equals to negative 80, right, times y. Okay, And because we're starting it from this point, so fx, fy, and fz will not have any moment, but tab and tac will have moment, right? So tab, if we're considering the y component and z component, so tab itself we have negative 2 over 3. Negative 2 over 3 tab, okay, which is in the y component, it won't cause any movement. Okay, we have 1 meter, so z component. Okay, so the z component is 2 over 3. So z component is 2 over 3. It can cause the signboard to flip up. Okay, it can cause the signboard to flip up. That means to say you can go counterclockwise. It's positive. So we actually end up having positive 2 over 3 tab, and the distance from the y to the signboard is times 2. Okay, and for here, for TAC, is just going to be positive 1 over 3 TAC times 2. Okay, so therefore basically we will have 2 over 3 TAC, okay, plus 2 over 3 TAC plus 4 over 3 TAB is minus 80 equals to 0. Okay, equals to 0. So therefore you can say that it becomes 2 over 3 TAC plus 4 over 3 TAB equals to 80. Okay, so let me just erase all this. Okay, so our equation here would be 2 over 3 TAC plus 4 over 3 TAB equals to 80. Okay, that's for mx. Now let's look as well. Let's look back again. Besides that, okay, so the thing is, if we consider the movement along the z-axis, so for the case that TAB, okay, it's 2 meters away from the axis, right? So TAB actually, the x component, right, the x component of the cable itself can rotate along the z-axis in a clockwise direction. Okay, it can rotate along in a clockwise direction. So we're gonna consider for mz as well. So basically our moment equation mz equals to 0. So by using our moment equation mz equals to 0, what happens here is that we have negative, our TAB is what in terms of the x component is 1 over 3, right? So negative 1 over 3 TAB, negative 1 over 3 TAB, and times with plus 2 meters. Okay, so you multiply with 2. Alright, and then for TAC, because TAC its x component is negative 2 over 3, right? But it's going to go in a counterclockwise direction. Okay, it's going to go in a counterclockwise direction along the z-axis to counteract the sign. So it would be minus 2 over 3. Okay, minus actually 2 over 3, because here's already negative 2 over 3, but we put a plus, so it becomes a minus. Negative 2 over 3 TAC. Okay, and it's also going to be 2 meters as well. So it's going to be 2 meters, which is equal to 0. So if you simplify the equation, you can see that you get negative 2 over 3 TAB, okay, minus 2 over 3 TAC equals to 0. So therefore you can say that yeah, that's basically your expression for mz. Okay, so you actually end up having 2 expressions regarding TAB and TAC. So negative 2 over 3 TAB minus 2 over 3 TAC is equals to 0. Alright, so now by having these 2 expressions of TAB and TAC actually, and if you solve these 2 expressions simultaneously, okay, so we take them simultaneously. So I'm gonna take this as by expression number 1 and expression number 2, and if I were to solve 1 and 2 simultaneously with simultaneous equations, by the way, so then you can easily get your TAB and you can easily get your TAC. So I'm going to solve it via calculator to save time, but you know, if you also have the time, you can also solve it manually if you like. So simultaneous equation, number of equations is 2. First equation, 2 over 3, 4. So TAC is actually minus 120 newtons and TAB is 120 newtons. Okay, so double check the answer first and see if it's right or not. So it's just 2 over 3 times negative 120 plus 4 over 3 times 120, 80. Okay, so we've already gotten our tension in the cable itself, which is just TAB is 120 newtons and TAC is negative 120 newtons. Negative here means that our assumed direction was wrong. So meaning to say that TAC actually, it's not really pulling from A. It's not actually pulling, by the way. It's actually more of like, you know, it's probably supporting it. And TAB is correct. It's pulling actually. Okay. So regardless, whatever values of TAB and TAC you have got, we just plug it in, and then eventually you can easily get your FZ. So your FZ is just simply gonna be what? If you want to substitute all the values in, it will just be negative 2 over 3, TAB is 120, and minus 1 over 3, TAC is negative 120. So your FZ would be, so negative 2 over 3, 120, minus 1 over 3 times negative 120, so it would be minus 40. So your FZ is minus 40 newtons, okay? So FZ is minus 40 newtons. And then also your Fy would be equivalent to 2 over 3, 120, plus 2 over 3, negative 120, which will turn out to be 0 newtons, by the way, yeah, because, yeah, with 0 newtons. So Fy is 0 newtons. And then your Fx, if you also substitute in, so Fx is just 2 over 3, negative 120, minus 1 over 3, 120. So how much would that be? So 2 over 3, let's see, TAC is what? TAC is, okay, so 2 over 3, negative 120, minus 1 over 3, oh sorry, 1 over 3 times 120. So it'll be minus 120. Okay, so I know it looks very messy actually if you're presenting it like this, but let me write it more clearly. So your Fx is negative 120 newtons. Okay, your Fy is 0 newtons. Okay, upon the computation, and then your Fz is negative 40 newtons. Okay, that's a support reaction at the ball and socket joint. Okay, then your tension at AB is 120 newtons. Okay, tension the cable is 120 newtons. Okay, and the tension at AC is a negative 120 newtons. Okay, so this is your final answer actually. Okay, for part B. Now going to the last part of question 2. What happened to the sine board in figure 4 if the force of magnitude 100 Newton is exerted at G in an upward direction? Okay, and why? Okay, so now question C actually is more of a conceptual question, alright, no calculation involved. So let's say you now exert, now what did they say? They said that what would happen to the sine board in figure 4 if a magnitude of 100 Newton is exerted at G in an upward direction? So you see this is point G, okay, where it's the center of the weight of the sine board, 80 Newton, right? So if we were to exert a force of 100 Newtons, okay, if we were to exert a force of 100 Newtons on it, what would happen to the sine board itself? So of course 100 newtons subtract 80, so the force at G becomes 20 newtons, right? It becomes 20 newtons. So that means the force at G becomes 20 newtons. What will happen to the signboard? So now, to answer for part C, okay, I'm going to answer for part C by the way. So this 80 newton is no longer 80 newton now, right? It becomes 20 newtons, alright? So your equation now is changed to 20 newtons. So therefore your... Wait, I'm sorry, hold up. Sorry. Your FZ is actually from B, yeah? It's actually not correct. I just made a mistake here. Because from part B, it's negative 80, right? So your FZ would have been FZ plus this one becomes 80, right? So it becomes 80. So now since we already found out that's the case, so FZ actually is going to be a bit... Your answer is not the same. So FZ is going to bring it here side plus 80, right? So plus 80. Okay? But this doesn't change your Fy and your Fx, by the way. I think this does not affect your Fx and Fy. So negative 2 over 3 times 120 minus 1 over 3 times negative 120 plus 80. So it's 40. So Fz is supposed to be 40 newtons. Okay? So Fz is 40 newtons. Okay? So let's see. Fz is supposed to be positive 40 newtons. Okay? So yeah, please update your answers. If you guys saw my answers wrong, it's actually supposed to be 40 newtons. Okay. So going back to a question, if we add 100 newton, right, at point G, so 100 minus 80 becomes what? 20 newton upwards. So you now it becomes positive 20. So that means that your Fz here become negative 20, right? However, for your Fx and Fy, nothing will change as of now. Okay, so nothing will change. But once you go to your Mx, okay, your Mx, because now it's going to be rotating upwards. Okay, upwards means it'll be rotating clockwise. So that means that it'll become plus 20, right? Plus 20 times 1. And then you have 2a, 3 over c, okay, and so on, right? This one was already considered. So plus 20, it'll be going upwards. So that means that here will be, that means if you transfer it here, becomes negative 20. Right? So it becomes negative 20. And once you solve the equation, that means what will happen to your tension? What will happen to your tension at TAC and TAB in this case? So if you do the simultaneous equation, if we were to solve the equation simultaneously, alright, which we'll do so, number of unknowns is 2. So 2 over 3 TAC, 4 over 3 TAB, negative 20, negative 2 over 3 TAC minus 2 over 3. So your tension actually become much weaker. Okay, so that means your tension, the cable, would become 30 Newton and negative 30 Newton. Okay, that means your tension will become much weaker. Okay, so if you apply an upward force, what happened to your signboard is that your signboard will start to rotate. Obviously your signboard will definitely start to rotate actually, because now it's in equilibrium. But if you apply an upward force, your signboard will actually start to rotate. Okay, and it will change your tension as well. But the main idea is, if you apply a force here, because right now it's in equilibrium, it's all static, but if I apply a force, it's no longer in equilibrium, right? You would have an excess of 20 Newton, which could cause the signboard to rotate upwards, right? You rotate upwards, that means you rotate along the x-axis, right? You have a, that means your summation of moment at x will actually not be 0 at this point, right? So this would mean that your cables might become loose, okay, and it can cause the cables to snap. Okay, it may cause the cables to snap. Okay, so what will happen to the signboard if the force of magnitude is exerted in G in upward direction? So the signboard will rotate. Okay, so you can say the answer will be the signboard will rotate actually. It will start to rotate actually, and because it will rotate, it can cause the cables, there's a possibility of the cables to snap, right? Because it's no longer in equilibrium. Alright, so because why? It's no longer in equilibrium. No longer in equilibrium. Okay, so this is your final answer. So it's no longer equilibrium, right? Because summation of mx is no longer zero, right? It's no longer zero once you apply the force, right? And of course, your summation of fz also is no longer zero as well, right? In this case, so this means that since it's no longer in equilibrium, can rotate, the signboard will rotate, and maybe possibly the cables may become loose, right? Maybe the cables become loose. Okay, so yeah, that's about it for question 2, right? We already covered question 2 already for ABC. So in the next video, hopefully we'll cover question 3 for this exam paper, and followed by question 4.
Okay, so question number 3 says if a 20 Newton force is applied to the handles of the pliers as shown in figure 5, determine the clamping force exerted on the wire at B. Okay, so this is the wire at B, and the magnitude and direction of the resultant force on pin A. Okay, okay, the first part. The second part asks to find the resultant internal loading of the cross section to point D of the pliers. Okay, so let's focus on part A first. Okay, so they wanted us to find the clamping force exerted on the wire at B and the magnitude and direction resultant force at pin A. Okay, so looking at these pliers here. Okay, so basically they wanted to find what is the clamping force at B. Okay, so uh basically we split these pliers into the simplest form possible. All right, so let's go to what I'm saying. So this question 3, part A. All right. So let me draw the pliers. So let me see the shape first. Okay, the general shape's like this. Something like this. Okay, let's see. Well, what's around there? Kind of close. Okay, maybe like you can probably modify a little bit. Okay, and yeah, you just draw it like so. Okay, all right. So let's label the forces. So the forces we have here is a 20 Newton. So I'm gonna write here there's a 20 Newton clamping force. Okay, this is 20 Newton. All right, and then we have the clamping force. So meaning to say that if we have the clamp acting, so that would this would be the force. Yeah, this would be the force at B. So this is FB. Okay, because think of it like this. Let's say if you draw the free body diagram of the pin itself, and you are holding the pin very tightly. Okay, FB and FB. So from the perspective of the pliers, right? If you're drawing one arm with the pliers itself, um, the magnitude is the same. So these two they have the same magnitude, okay? But the direction is different. So this one's obviously in the opposite direction. This is going upwards. This is going a bit downwards, okay? So that's why I drew it like that as it is. All right. And then what else also we have here? Let's see. Uh 120 millimeters from the force 20 newtons to the pin at A. Okay, so let me mark this pin here. Okay, to the pin at A. So you'd have the forces here is AY, and let's just say this is AX, and the distance between those two, okay, is let's say 120 millimeters. Okay, how else? And then uh let's see. Basically from A to B it's about 40 millimeters. Okay, from A to B it's about 40 millimeters. So from A to B it's about 40 millimeters. Okay. Let's see. Is there anything I missed out so far? This 15 millimeters from C to B is irrelevant for our case because it's not important to us. And this 80 millimeters from the 20 Newton to D, this is not relevant to part A at the moment, okay? We'll later see it more in part D, okay? And is there any height difference? So there's no vertical height difference between. Is there any height difference or not actually? Seems like there is, but wait, let me have a look first. Is there any height difference or not? 120, 80. Uh, no, no height differences so far. Okay. So actually, I think it'll be a fairly easy problem. We're just supposed to find FB and we're supposed to find AX and AY. So if you recall from your equation of equilibrium, okay, so we know that summation of Fx equals to 0, okay, in the positive direction. Summation of your Fy also equals to 0, and summation of your moment, if you're taking the counterclockwise direction, is also equals to 0. Alright, so you denote this as your positive x and your positive y. Okay, I think it's fairly quite straightforward. Okay, so if we were to go with summation of your fx equals 0, so that means to say that's only just ax equals to 0. Okay, so ax is equals to 0 newtons. Alright, so that's your ax. Then if you were to take the moment, okay, at point A, okay, I prefer to take the moment at point A equals to 0. So that means to say the 20 newtons times 120 millimeters, okay, it's going counterclockwise. Alright, it's going counterclockwise, so it's positive. Whereas this FB is going clockwise, so it becomes FB minus 40 equals to 0. So therefore, you would have here 40 FB is equivalent to 20 times 120, so that would be about 2400, so that would be 2400. So your FB would be equivalent to 2400 divided by 40, so therefore dividing by 40 would become 60. So the clamping force acting on the wire is 60 newtons. Okay, and then last but not the least, you use your Fy. So your summation of Fy equals to 0. So therefore, in this case, it's just simply negative 20 plus Ay minus 60 equals to 0. So Ay is just equals to 20 plus 60. So 80 newtons, okay? So yeah, this is your answer basically. Okay, so your AX is 0 newtons, your FB is 60 newtons, and your AY is 80 newtons. Okay, let me just double check and see if I got everything right so far. Okay, yep. So it's pretty simple actually, a fairly straightforward question for part A. You just draw the right free body diagram, which in the case is this one, obviously. And this is not really necessary, it's not very helpful free body diagram by the way, so yeah. And if you draw the other arm also, like whether which arm you draw, since I chose this arm to draw, okay, even if you were to draw this arm, the results are still the same, okay, because the loading is still the same. You'll have the pin force at A, you'll have the 20 newtons, and then you'll also have the force at B, right, the contact force or the clamping force as they call it. Oh, they want the magnitude and direction of the resultant force on pin A. Oh, so the magnitude, direction, resultant force on pin A. So actually the answer is partly complete. Okay, so if you want to find the overall resultant force of pin A, so I'll just call it as A. So A is just simply the square root of 0 squared plus 80 squared. Alright, which is equals to 80 newtons. So that's the magnitude of the resultant force. The direction is clearly going upwards. Okay. So yeah, this is basically the final answer because for resultant force, if you want to find resultant force, is basically the square root of your x component, a square root of your x component squared plus your y component squared. That's the magnitude, okay? And direction, uh, you know, the direction actually normally would have a direction which I think I'll probably use in white, by the way. Let's say, for example, if ax is not 0, okay, and let's say you want to find your a. So for direction, that's theta, okay, for reference to the positive x-axis. So you can say theta is just basically tan inverse your y component, okay, over your x component, right? That is if, again, as I said, that is if, ax is not 0 and you have to find the direction. So that's how we would do it, okay? So we don't need it in this case, right? So it's pretty straightforward. So let me just erase it real quick. Give me a few moments. Right, so I'm back. Okay, so right, let's go to question B. Question B asks you to determine the resultant internal loading on the cross section through point D of the pliers. Okay, so they wanted to find resultant internal loading. Okay, interesting. So let me erase this. Okay, they'll make the eraser a little bit bigger. Let's see. Okay. Oh, sorry, don't know if I've used yellow, I guess. Okay, cool. I'm gonna keep the answers from FB, yeah? I'm just gonna keep the answers from FB and for A, okay, the resultant force for A and FB, in case if they are needed, okay? In case if we need them for the later part of the equation, okay? This is from part A, by the way. Okay, so I'm gonna erase this. The question asks us to determine the resultant internal loading on the cross section through point D of the pliers. So basically, if let's say we take the pliers, right, after we found the A and FB, we would section it and we would try to find the internal loadings. My advice again is that when you are sectioning to do internal loadings, pick the one which seems the least complex, meaning to say there's very little loadings actually, because the internal loadings on both sides would be the same. So I'm gonna pick the one on the left, okay, which is a 120 Newton because that's the only force, so it's less complex. Whereas if let's say I were to pick the one on the right, I would have to consider the pin force A and the cutting force B, so it seems like a lot more, that's why I prefer to take the one on the left. So that's exactly what I'm gonna do. I'm gonna draw a free body diagram of the same pliers, okay? I think I'll just stick to blue. Alright, let's use blue. Alright, okay. So, okay. We're sectioning one side, yes. And our force here is 20 newtons. Okay, so just simply 20 newtons. Alright. And when we sectioned it, by the way, we sectioned it. This actually, when we section it, it has an angle, okay, of 30 degrees, okay, from the normal y-axis, okay, so compared to here just now, compared to the vertical, all right, the angle here is 30 degrees, okay. So we take the positive x and y convention, okay, as usual, and once we draw the internal forces, so this would obviously be our normal force, right? And I'm assuming since this positive direction, this would be our shear force, okay? Okay, and our bending moment, we need to say that would be here. Okay, so this would be our normal force at point, what's the point? Point B, a point D. Okay, so normal force at point D, shear force at point D, and bending moment at point D. And our distance from this 20 Newton to the plane itself is, uh, okay, actually from here to this point itself is already 80. Okay, 80. Okay, so this is about 80. All right, it's about 80. Okay, so now there comes an interesting question, right? So how are we going to determine our bending moment? Okay, our normal force and our shear force. Okay, because it seems a little bit tricky. Um, okay, so if let's say I were to take the moment at point D, okay, let's say if I take the moment at point D, okay, for instance, so I'm going to take the moment at point D to be 0, okay, so I don't have to worry about the normal force and the shear force causing any moments, right? I only have to worry about the bending moment and the 20 newtons. So in this case, uh, the 20 Newton force is going clockwise, so it becomes negative 20 times 80, okay, plus the bending moment itself, which is just md equals to 0. So therefore, md is just equivalent to 20 times 80, which is 20 times 80, which is about 1,600 Newton per millimeter. And if you want to convert it to Newton per meter, you just simply divide by 1,000. So it's just simply 1.6 Newton, 1.6 Newton meter. Okay, so that's your bending moment. Pretty simple. Now for your normal force and shear force, you actually have to use your other two equations of equilibrium. So basically your Fx equals to 0, which is obviously on this side. Okay, so this 20 Newton actually is clearly going in the y-axis, so there's nothing about it in the x direction. So we have to resolve the other two. So in this case, our VD, okay, VD has a cosine component that's going downwards, okay, that's going sort of downwards, okay, which we're not interested. But it also has a sine component as well as going the positive direction, the x-axis. So it would just be VD sine 30, okay, and our ND, okay, because our ND also ND also, by the way, is also influenced by 30 degrees as well, so it also has an influence of 30 degrees. Okay, it's all trigonometry. The cosine is going to go upwards in the y direction, but the sine is going to go in the right hand side, so it's going to go in the positive x-axis. So plus ND sine 30 equals to 0. So sine 30, we know sine 30 is half, so it just simply become half VD minus half plus half ND is equals to 0. So therefore, if you bring it to the side, it becomes half VD minus equals to negative half ND, and your final expression would just simply be VD equals to negative ND. That's equation 1. So I'm going to erase all this, and we're going to simplify it just like that. Okay? So it'll just simply be VD is equivalent to negative half ND, negative ND. Okay? So that's your summation of fx. Now for summation of Fy, okay, if we take it to be positive, alright, so we of course have 20 Newton going upwards in the positive direction, and then our VD, since it's going downwards, okay, because if you have a cosine 30, so it becomes minus VD cosine of 30 degrees, okay, and then ND, because it's going upwards of cosine 30, right? So In this case, it would be plus ND cosine of 30 degrees equals to 0. Okay, here's the catch. Because remember that in our expression that VD equals to ND, negative ND, I'm going to substitute uh, ND, I'm going to substitute VD with negative ND. So it become 20 minus negative ND, okay, cosine 30 plus ND cosine 30 equals to 0. So negative, negative become positive, and plus with ND, you just simply get 2 ND cosine 30 degrees, okay, equals plus 20 equals to 0. So upon rearranging the equation, or rearranging the expression, you would have ND as negative 20 over 2 cosine 30 degrees. Okay, so just simply be negative 20 over 2 cosine 30. So just simply become negative 11.5, yeah, 11.547, but we're just gonna write as negative 11.5 newtons. Okay, the negative meaning to say that our direction was assumed to be opposite of what we thought initially. So that's for your normal force. This is still in newtons, by the way. So that means that your VD, okay, negative negative become positive, so 11.547 newtons. So just simply 11.5 newtons, and it's assumed to be in the correct direction as before. So that's your shear force. Okay, so your normal force is negative 11.5 newtons, shear force is 11.5 newtons. Okay, and bending moment is 16.9 newton meter, 1.6 newton meter, right? So it's going to be also in counterclockwise direction. Okay, so let me just double check. Okay, yeah, that's pretty much about it for question 3. We've already finished part 3, and as promised, we're going to part 4, the last part of the paper. Okay, so here's question 4. Right, so they asked us to refer to the structure shown in figure 6. Two identical boxes A and B have the same mass of 100 kilos and are stacked as shown. Okay, so it's stacked as shown. So question part A asks, what are the 4 possibilities can happen if force P is large enough to cause a motion? Okay, so let's go and discuss this actually. Okay, right, so let's say for part A, okay, so for part A, let me just erase, I don't know what's happened here. So for part A, okay, so the question is asking what's likely to happen, what are the 4 possibilities, okay? So let's draw the boxes first, A and B. Okay, let's pretend this is A, then let's pretend this is B. Okay, so A and B. Okay, and we have a force of P that is acting on the box. Okay, so what are the 4 possibilities that could actually happen? Well, it's quite simple, really, right? The first possibility that could actually happen is that if A were to slip off from B, okay? So meaning to say that you apply a force P, okay, and box A would just slip off from box B, okay? So basically, the force P is enough to push off box A. So meaning to say, it would slip A from B. That's possibility number 1, okay? What would the second possibility? The second possibility is it can, okay, whoops, I used the wrong color. So the second possibility is this. Maybe the force P is large enough to tip box A, okay, it's enough to tip box A off box B, okay? So it's large enough to tip box A off box B. So basically, that's the second possibility, right? Tip A from B. So what about the third possibility? The third possibility is that it can push both box A and B. Okay, so I think I forgot to draw a surface actually. Put green, 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 and green actually. So what's gonna happen is that, yeah. So basically you can push both box A and box B. So box A and B would slip off from the surface, right? So yeah, this is basically box A and box B. You apply a force, okay, of P. So basically both box A and B will move. Alright? And the last option is that maybe the force is strong enough to cause both boxes to tip over. Okay, so that's a possibility too, right? So I think okay, so this is B. And maybe it's just enough to tip them over. So the last possibility is both box A and B will tip on the surface, right? Okay, so again, these are the four possibilities. Either A would slip from B, mean like to say that A would move on B. Either A would be tipped off from B, box B, or it could be that both box A and B will move or slip. Okay, it can slip from the surface, right? As you can see, it moves from here to there. Or the force is large enough to cause both box A and B to tip on the surface. Okay, so these are the four possibilities that are likely to happen if force P is large enough, right, to cause one of these things. Okay, so there easily that's your 8 marks. Pretty simple. Now, if the coefficient of static friction between the boxes UAB, that means this coefficient of static friction is 0.8, and between the box and the ground, so between the box and the ground is 0.5, determine the minimum force P required to cause impending motion. So cause impending motion. The word here is to cause impending motion. Okay, so if it's about impending motion, that means to say that it's about to slip. It's not about to tip, okay? And what would happen if the force P exceeded the value? Okay, so what would happen if force P exceeded the value? Okay, so the word is impending motion. So if they said the word impending motion, that means the motion required for the box to, you know, to slip. Actually, yeah, I think that should be about it. Okay, and then for part C is a different question. But let's go to part B first of all. So, all right, let's. That means we have to take an assumption of two cases actually. Okay, so let's go to part B. Because the word says impending motion, that means it's gonna be slipping actually. It's gonna be slipping. That's gonna be important here, right? So the first assumption, okay, the first assumption is what? First assumption is we assume, sorry, assume box A slips slips from B. Okay, so if we draw box A again, let's just draw box A. Okay, and then we have here box B. Right, so this is box B, and this is our grass or ground surface. We apply the force P. Okay, and the force P is 5 meters. Okay, which is not really that important to us, honestly. I think 5 meters is not really a big deal because we're considering about box A slipping, so dimensions is not a very important thing at the moment. Okay, so that means there's a frictional force, right? This frictional force, by the way, and of course, box A will have its weight. I think they mentioned the. Did they mention the weight of? Okay, the two identical boxes have the same mass. Okay, so meaning to say it has its weight. Okay, great. So I'm gonna mark it in yellow, I guess. Okay. So box A has the weight, obviously. Okay, and that weight is you know, obviously it's just 100 times 9.81, right? Which is 98.1 Newton. And of course, you would have the normal force, right? And R. Okay. So if we were to solve this equation, okay, if we let's say we were to solve this equation, okay, so from the perspective of summation of Fy equals to 0, okay, from this equation, all right, we can see that nr minus w equals to 0, okay? So basically nr equals to w, which is 98.1 Newton, okay? And then from the perspective of the summation of fx equals 0, okay? Well, I forgot to actually put the positive x and positive y, yeah, to show the direction. So in this case, we know it's just going to be p minus f equals to 0 and p equals to f. Okay, here's the thing here. This f, because we're assuming it slips, right? So this means to say that this f is equivalent to us and r. It's a maximum frictional force. So what is our us? Basically, our us is 0 0.8. Okay, so it is 0 0.8 times nr, which will of course I'll show you in a while, right? So yeah, we'll just put nr for now. Okay, so this p is equals to 0 0.8 nr, which is just 0 0.8 times 98.1, thus giving us a final answer of 0 0.8 times 98.1. It's 78.48. Okay, so 78.48 newtons. Okay, so from our first assumption, okay, our first assumption, what can we conclude? We can conclude that our first assumption actually, the answer is 78.1. Okay, so I'm just gonna probably write it. I think you can just put it here. So the assumption is that P equals to 78.48 newtons. Okay, all right. So that's the first assumption, right? Oh yeah, first assumption. And then now let's compute for the second assumption. So let's erase that. So for the second assumption, what's going to happen? So we're going to assume both A and B slips. We need to say both A and B would move. Okay. So in this case, what's going to happen is that we're going to have here forces of A. Okay. And for example, box B. Okay, I think that was pretty big by the way, but never mind, no worries. And we apply the force P on the box, on both of them. Okay, and of course there'll be a friction at box B, right to the surface, which is F. And we have the weight of two boxes combined together, which is obviously going to be um, W, which is in this case, since A and B are both 100 kilos, so in total is 200 kilos times 9.81. Okay, therefore our final answer would be 200 times 9.81, which is 1962. So it's 1962 newtons. Okay, so of course that means you'll have your normal force nr, right? So okay, that means to say for your Fy, Summation of Fy equals to 0. Okay, remember that your x positive is to the right, y positive is upwards. So what we can say is that uh, your NR minus W equals to 0. So therefore your NR is equals to W, which is obviously 1962 newtons, right? And then for summation of your Fx equals to 0, okay? So we know that P minus F is equals to 0 and P equals to F. And remember, because we're assuming that both boxes slip, so this F is basically the maximum static frictional force, F max, okay, which is just simply 0. I think they mentioned it was 0 0.5, okay, so 0 0.5 and R, so it's just simply 0 0.5 times 1962, okay, so just 0 0.5 times 1962, so it's a 981, okay, so it's 981 newtons. So therefore, the second assumption that if both A and B were to slip, your force would be 981 newtons. You need about 981 newtons. Anything past that force, then both of the boxes will start to move. Okay? So that's the assumption. Now going to assumption number 3. Okay, so I think I'm gonna have to write this a little short here because of space issues. But okay, so I'm gonna write it like this. So assumption 1, I want you guys to remember that for assumption 1, so assumption 1, okay, our P was equals to 78.48 newtons. Okay, this is basically box A slips. Okay, and then assumption 2, which we'll be writing as A2, your value for P is equivalent to 981 Newton. Both A and B slip together. And B slip together. Okay, so I'm going to erase this. So for space purposes. Okay, so now assumption number 3. Okay. Oh, sorry, what is assumption 1? A1. Assumption number 3, we are yet to find out. Okay. This is the case when, um, of course, this is when box A tips, right? So box A would tip. So in this case, if we drew the free body diagram, so it's when box A is tipping. Or actually, I would rather not draw it like this. Rather draw it like this. A is tipping. Okay. You don't have to draw B, by the way. So you can draw the force P. Okay. And the force P from box A, that's 5 meters. Here is 4. So therefore, from here to here is 5 minus 4, which is obviously 1 meter. Okay, so that's where dimensions are important. This is 1 meter. And here is 3 meters, and here's 4 meters. Okay, great to know. So here is 3 meters, and the whole thing is 4 meters. Okay, excellent. So we'll obviously have the frictional force, which I think I'll be highlighting it in green. Okay, so it's the frictional force. Okay, and the reason I'm considering the tipping, actually, initially I was planning to only consider slipping, but I realized that actually impending motion can, in this context, it can be a general case. It can either be tipping or it can be slipping, right? So we also do have to analyze for the cases of tipping as well. Okay, and this is our frictional force. Okay, and this is our normal force. So our normal force is nr, and then our weight is, okay, it's right here, which is just w, and the distance from the weight to nr, okay, or from the center of the box to nr itself, it's about um d, which is obviously 3/2, okay, or 1.5 meters. Okay, so if we take the equation of equilibrium at the let's say at a particular point, I think I'll take it at this point right here, which I'll call it as point O. All right, so the summation of moment at point O is 0 counterclockwise. So that means the effect of normal force and friction are not really considered. So therefore it'll just simply be the weight and um the force P itself. All right. So from weight, since from the weight to point O, the distance is just simply 1.5 meters and it's going in a counter clockwise direction, okay? So it will just simply be 1.5 W, okay? And then for P, okay, from point O is a distance of 1 meter, it's going in the clockwise direction, so it'll be minus P equals to 0. So therefore, P equals to 1.5 times W. So our W is, since it's a 100 kilo box, right? Times 0.9, so it's 100 kilos times 0.9, sorry, 9.81, right? mg. So our P would be 1.5 to the 100 times 9.81. So it's actually pretty large though. It's about a 1471. Wow. 1471 1471.5 newtons. Okay, so therefore, our assumption 3, if box A were to tip, we would need a force of 1471.5 newtons. Okay, which is quite a lot actually. I probably have to write down. So 14.5 newtons. So this is just only box A tip. Okay, now we're coming down to our last assumption. Okay, so assumption number 4, basically, this is the case when both the boxes were tipped. So basically, both A and B will tip. Okay, so how do we do this? Okay, quite quickly. So this is your B. Okay, this is your A. Okay, and this is your surface. Okay, and I'm going to put this point here. This is where point O is going to be. And this is our normal reaction force. This is our friction. Almost looks like P, right? Let me just change that writing. Okay, suppose this is your friction. And this is your force P. Okay, alright. And this is your weight. Okay, so the weight is... So your weight's actually... Well, because you see, these both boxes are rectangular, right? So your weight for a rectangular, for two rectangles, actually is in the center of the rectangle itself, okay? So it'll be around here. Obviously, which is just simply 4 plus 4 divided by 2, so it'll be 8, okay? So it'll be around here, and this is going to be your weight, okay? So it's going to be your weight. All right. So here, the distance is 3 divided by 2, which is just, 3 divided by 2, which is just 1.5 meters. And here, I think they really explicitly make it clear it's 5 meters. Okay, so it's only 5 meters. And yeah, that's pretty much about it. If we were to take the moment at point O, okay, we take the moment at point O to be 0. Okay, so basically the effects of normal force and frictional force are not counted. So what do we have here? Okay, I think I'm going to use a different color. I think I'm going to use gray for now. Okay, so basically we have the weight with the point O, right? Which is going to obviously cause a counterclockwise moment, right? So in this case, that would be 1.5 times W. Okay, but for P, for force P, at point O, the distance is 5 meters and it's going to create a clockwise moment. So it'll be negative 5P equals 0. So we would end up having 1.5 W equals to 5p. Therefore, our p is just, 1.5 W divided by 5. And of course, if you want to simplify that further, 1.5 divided by 5 would be obviously 0.3, right? So it will just simply be 0.3 W. So what is W? So W, because we have two boxes, is 200 kilos times 9.81. Okay, so if you were to calculate it all together, so 0.5 times 200 kilos times 9.81, it's 981 newtons. So interestingly, um, it's 981 newtons. Wow. So basically, 981 newtons, if you were to apply this force, it would either cause A and B to slip together or and tip together. Well, that's a bit interesting actually. Huh. All right. So that's about it for assumption 4. So now let's look what the question is really asking for. So the question's actually asking for determine the minimum force P required to cause impending motion. So what is the minimum force that's required for A and B to move? And the minimum force, the answer is assumption 1. Okay? Where box A will only slip. Okay, that's basically the minimum force required. So your P, if you run into three significant figures after all that calculation, is 78.5 newtons. Okay, so this is the minimum force required, and the question asks what happens if force P exceeds that value. So your answer should be if force P were to exceed the value, what happened is that box A, okay, will slip from box B if P is larger or greater or equals to 78.5 newtons. So this is basically a final answer for question B, okay? The calculation isn't complex, but the fact that you have to fulfill or check for all assumptions A1, A2, A3, and A4, okay? So that can be a bit tedious. Alright. Going to part C, the last part of the question. If the coefficient of static friction between the boxes UAB is 0.2, will it be harder to cause motion for box A? Previously it was 0.8, right? Now, if we think that P is 0.2, so what's going to happen? Okay, let's go back to part C. Okay, so now if we were to draw our free body diagram for this box A only, okay, we include all the relevant forces. This is force B, friction force F, okay, and what is this supposedly? Your weight, okay, and of course your normal force, right, which is obviously going to be the normal reaction force, okay. So in this case, right, we know that our static frictional max is 0.2, and R, right, and we know that NR is equals to weight, which in this case is just simply 100 times 9.81. 98.1 newtons, right? So your frictional force would be equivalent to 0.2 times 98.98.1, which would give you 19.62 newtons. So we also know that P equals to F, so we need to say that it's just 19.62 newtons. So the answer is, no, it won't actually be harder. So the answer is no. It'll be easier actually. No, because the minimum force required, okay, to cause box A to slip has decreased, right? Has decreased significantly, right? It has decreased actually. Has decreased significantly. Okay? Since has also, since it's the coefficient of static friction also decrease, right? Because you see, previously we were working with UAB was 0.8, okay? But now, since we reduced it to 0.2 rather than 0.8, so therefore the frictional force that's acting between A and B is far less. So you only just need 19.62 newtons, basically roughly about 20 newtons of force. You only just need roughly 20 newtons of force just to push box A out of box B. Previously, you need roughly about 98 newtons, okay? So, yeah, it's a huge reduction actually, a huge reduction in terms of the forces you need. I would say it's probably, if I'm not mistaken, 98.1 divided by 19.62. Wait, is it? No, sorry. 78.48 divided by 19.62. Yeah. So basically it's one fourth actually. The reduction is huge because your coefficient static friction 0.8, if you were to multiply by that by one fourth, which we got 0.2, right? So because your coefficient static friction was decreased by one fourth, right? So your force also that's required to, you know, push the box initially 78.48 is now reduced by one fourth. Okay, so it actually becomes much easier the for box A to be moved. All right, so I think this concludes the end of the past paper, right? So this is the end of the past paper where I've done all four questions. So as you can see, so far I think question 3 and question 4 didn't really took that long, but question 1 and question 2 seem to took a bit of more time for me actually. I think maybe because of the center, maybe it took me some time to sketch the shape, I guess. But yeah, I can see that question 2 might take a bit of time, especially the 3D figure. You need to really think it through, all right? Question 1 also does require a bit of thinking because which element you want to use and the integration and such. And also this one as well, moment of inertia for composite bodies where you have a hole, you have a trapezium, so you have to make it to a right angle triangle, right? And actually question 3 was surprisingly quite easy, like it's actually pretty straightforward, you know, and you basically get 3 marks. And question 4 also wasn't too bad. I would say question 4 is quite a balanced question. It's quite a well designed question actually. So yeah. So hopefully this exam simulation, or not really call it more of a simulation, more of a you know tutorial, I'd rather say it, has helped you guys to prepare well for your final exam. So I do wish you guys all the best. All right. So good luck for your finals, obviously, right? And yeah, all the best.